Methodical, analytical neural networks are highly capable of processing raw information, but they often scale by firing randomly and expanding without structural boundaries. The core problem with this unconstrained growth is that it fails to mathematically connect raw data processing to socioeconomic responsibility. The machine learns, but it does not inherently understand the boundaries of human cooperation. Over a decade of research at Richard Systems has focused on a specific thesis. True AI resilience requires mapping neural network architectures directly to proven models of human cooperation. We engineered a solution called the Survitality stack. It is divided into 3 distinct layers. The infrastructure tier parses raw data, the governance tier binds that data to strict behavioral rules, and the application tier deploys those rules to manage real-world resources. Achieving true resilience cannot be done with a superficial patch at the model level. It requires a unified pipeline built from the ground up, linking raw serverless logic to strict behavioral agreements. At the foundation is Layer 1, the infrastructure tier known as Cortex.io. Its primary function is to apply a process called primal semantic lean to process massive streams of unstructured events, such as ISO 31000 risk management news feeds. This schematic outlines the strict microservice time constraints used to route incoming data. Tasks are divided into 2 distinct pipelines. Lightweight semantic algebra tasks are routed specifically to this short circular loop, executing entirely within sub-15-minute AWS Lambda functions. Heavy, sustained processing tasks that exceed that window require the dedicated AWS batch Fargate pipeline to handle the denser payloads. Both pipelines ultimately consolidate their outputs. The system's storage architecture migrated from an elastic stack to this federated vector database lakehouse to improve retrieval speeds. This infrastructure layer acts as a macro synapse. It converts raw, chaotic text into a highly structured, tokenized on-primes data model, preparing the information for the behavioral calculations that happen next. Moving up to Layer 2, which we call responsibility futures, we establish a necessary boundary. Perfect data architecture is useless if it is not bound by strict behavioral limits. This is the primary governing equation for the system, the calculus of choice. We define responsibility, the R variable, strictly as a mathematical function of intention divided by negligence. By weighing these specific submetrics, the machine evaluates behavioral outcomes. This split screen illustrates the challenge of translating abstract policy into machine instructions. To compute these variables, we convert standard policy documents into executable predicate calculus. We enforce these logic gates using the 9 constraints of AI. These serve as the absolute boundaries governing the predicate logic. To test and validate these mathematical constraints dynamically, we run them through social agent-based models, tracking how independent entities negotiate resources under the rules provided. This layer solves a massive problem in AI development by moving governance from philosophical theory into executable math that an autonomous system can optimize. We deploy these mathematical governance models in Layer 3, the Survitality applications tier. Here, the theory is piped directly into operational dashboards, like integral manufacturing and shared services, or IMaaS. To scale this system effectively across localized networks, we apply a specific socioeconomic constraint, the Dunbar calculus of value. This node graph illustrates the Dunbar limit. A central hub can maintain stable resource connections up to exactly 150 surrounding nodes. Any connection attempting to scale beyond that threshold glows red and is severed by the system to maintain network integrity. Within those 150 verified nodes, we use put options on loyalty. Tracked on ambient Gantt charts, these allow localized networks to lock in future choices through verifiable agreements, ensuring predictable cooperation over time. These macroeconomic tools translate precisely into hyperlocal edge nodes, giving us the architecture to establish family fire data standards and localized digital twins. This schematic shows the physical manifestation of those digital twins. Real-time resource metrics are applied directly to real estate management, optimizing the footprint of a compact tiny home. Macro-level AI tools realize their intended purpose only when they successfully manage and optimize micro-level human cooperation. Zooming out, we see the fully integrated Survitality stack, built over the last 10 years. We trace data processing from the infrastructure layer's vector database up through the governance layer's predicate logic, before finally arriving at the application layer's ambient Gantt tools. Cortex.io's semantic algebra acts as the engine, providing the processing power, but the responsibility index acts as the steering wheel, providing the direction. This framework sets the foundation for our future deployments, specifically agentic procurement protocols and humanitarian gambits. The ultimate end state of this technology moves past raw machine learning and into a system of highly coordinated machine loyalty. This is algorithmic vitality, an era where autonomous AI systems operate explicitly within the engineered certainty of verifiable human agreements.